Welcome back to my channel. This time I'm gonna show you all a little project I recently finished. And it's exciting because I can walk you through the entire process of designing the electronics, the CAD, and writing the code for it. I'm super excited, I hope you too. Let's get started. It all started when I was researching equipment for recording videos like this, and I came across repeatedly these what I call influencer lights. It's basically a phone-sized LED matrix with RGB LEDs on it and a little battery attached to it, and you can basically just choose the color you want, mount it on a tripod, and then you have a lighting solution. I thought it would be an easy project to get started. I thought it would take a couple weeks, a month tops. Fast forward to 5 months, I'm now at a stage where I think I can show it. So let me walk you through it. And here it is, neon. It's a PCB with RGB LEDs on it. It comes with a battery and battery charging. It does have Wi-Fi and a web interface to remote control it. It comes with a number of physical buttons to control it just at the device. So let's quickly turn it on. And we can choose from a number of colors. We can change the brightness. And it also comes with a 1/4-inch thread that threads on these common connectors for cameras and lights and other devices. You can just put it there and use it. One thing about LEDs is that I'm using these strips, and that is much nicer because I don't need to solder on each individual LEDs. Instead, I can buy these meter-long strips, cut them to length, and just need to attach them at the very end to the PCB. What's nice about it is that it makes the PCB single-sided. I only need to populate parts on one side and can then reflow it. Let's first take a quick look at the schematic and then at the layout before we go into CAD code. We're getting data and 5 volts from USB-C. We have a LDO to generate the 3.3 voltage for the IC. It's the first time using an LDO for me. This particular one is a relatively juicy one. It, if I remember correctly, can output 1 amp, which is more than enough for what we need here. But I want to use the same chip in other designs, so I thought I'd go with a little bit of a more powerful one. The enable pin is directly connected to a physical switch, and that allows us to turn on and off the board with a switch. Something that is worth mentioning is that we have a dedicated voltage here that is either the voltage from USB-C, the 5 volts, or the voltage from the LiPo battery, something like 4.2 volts. And it's done by these 3 devices here. And we use this VD to, yes, input into the LDO and to generate the 3.3 volts, but we also use it for the LEDs. So all LEDs are connected to VD, meaning that they basically run off USB-C if it's connected, and otherwise just the battery. Lastly, in the power section, we have the LiPo charger. It's also the first time for me to use LiPo charger. This one, I picked this particular one here because it can charge at 1 amp. Given that we have a relatively beefy battery in the pack, that's a good current we want to use. A little circuit, a little voltage divider just to measure the voltage of the battery. And then we have the IC. So I'm using the ESP32S2. This particular one comes with 4 megabyte flash, and we have just a couple of decoupling capacitors and in here for input voltage. This is all to spec. you just find it directly in the documentation for the microcontroller. We have a little circuitry that is demanded by the spec as well, so nothing fancy here. There are two things to call out here. Number one is the antenna and the way it's connected. We have this matching network here that is needed to match the impedance that the antenna and the microcontroller require. You choose each of these components, each of the capacitors and inductor, to have certain values to match the impedance of your system. The problem is that the impedance depends on a number of things, including the microcontroller, the antenna, the board layout, and even the components themselves. So what you really need to do is you either have a board layout that you know that works, and then you can try to just copy the values of that known layout, or you would need to use a testing device to basically ensure that you have matched the impedance correctly. And I have neither of that. What we do for now is we just don't have a matching network. So we don't populate the capacitors, and we make the inductor here just a jumper, a 0 ohm resistor. And it works. It's not perfect, but it works fine. The second thing we're talking about is the crystal. It's needed to generate 40 megahertz signal for the IC. What's challenging about it is that it needs these two external load capacitors. There's a formula to calculate what these external load capacitors should be. The problem is that it requires the stray capacitance, and the stray capacitance is not known to us. It depends on the board and the board layout, so we have to guess. It's somewhere between 4 and 8 picofarad most of the times, so I have read. So I just put pick 6, and we arrive at 18 picofarad for our external load capacitors. One thing to point out here is that if we choose crystals with an internal load capacitance that is high, that means that getting our stray capacitance wrong has a smaller impact. So I choose this particular crystal here because it had a relatively high load capacitance. And in this, this particular assembly works fine. It generates perfectly fine 40 megahertz. That's it for the IC. We have a couple of default on buttons. We have one button that is used for the GPIO 0, that is used for the bootloader to decide whether to go in a certain boot mode or not. I didn't have this button initially, and it meant that I needed to manually go with a microscope and a jumper wire to connect these GPIO 0 to ground when turning it on. It was quite a hassle. Now I have the boot button, so that's not a problem. We have a couple of flags just to appease the ECR, and then the connectors for the LED. Let us now take a quick look at the layout of the PCB. Something that is always useful to have a quick look at is just the 3D rendering of the layout. This is the back side where the LED strips will go, and on the front side we will have a place for the battery, our physical input buttons for controlling the light source, the physical switch for turning it on and off, the USB-C connector, the boot button that I was talking about, connectors for two kinds of batteries, one that just comes with a plus and minus, and one that comes with a dedicated line for the internal temperature sensor. I thought it's fun to just try to use it. It's also the batteries I could find, the juicier ones always had these three connectors. And then up here we have all the microcontroller and all the ICs we need just to run the board, including the antenna that is at the top here. Looking at the layout, I think there's nothing super crazy here. The only challenge I had is to route the various capacitors and the various lines to the capacitors for the microcontroller for the ESP32S2, mainly because the reference design is using 0402 components, so they're even smaller than the 0603 components I'm using, and that makes my layout just different to the recommended layout. But all in all, everything is working, so I think that is something not to be too worried about. And 0603 is a size that is actually very possible to populate by hand. 0402, and I use 0402 components for the imaging network for the antenna, they are tiny. They're really hard to place, so I'd rather not use them. One neat thing that you can do is you can create a preset of filter layers that just shows you the outline of each component, of each element, its label and the nominal value, like 1K in this particular case, which I found very easy to use when populating the board. That's pretty much it for the PCB layout. The last thing to say is that this is a 10 by 10 PCB, so 10 centimeters by 10 centimeters, which is the largest size you can get from the common PCB manufacturers like JLC PCB and PCBWay for relatively cheap. Next up is assembling the PCB, and I'm using the stencil fix that I have created in the previous video, and I'm really happy how that is working. It's so much simpler to apply the solder paste, and the result is really good. All that's left is now to place the components on the PCB. It takes quite some focus to not place the components on the wrong pad, so I have to double check a lot with the schema and the layout to ensure that I'm really placing the right components. Here's a view through the microscope. All the components are placed now and are all looking pretty good. The thing I'm super happy about is how well the solder paste was applied. And onto the reflow oven. This is used to heat the PCB up following a temperature curve so that the solder paste can be reflown and the components are soldered in place nicely. And here is a view after reflowing. All the components are soldered in place very nicely, no solder bridges, which is particularly important for these fine pitched components. Let's quickly look at the design of the case. There's not too much to talk about except for one or two points. First being that I used KiCad to export an STL of the board so that I knew where to make cutouts for various devices. One other thing maybe to quickly talk about is just the word neon at the back of the case. It's not actually a font, as you might have guessed already. It's just a little bit of geometry. Everything is kind of determined by just the height of this bar and the width, and yeah, everything else is just derived from that. And I think that turned out pretty nice. Obviously for more complex text I would try to go with a different approach, but the idea here was to imitate how one would write the word neon with actual neon tubes. Just a little fun fact. So the case is yellow and the web UI is yellow as well, but pure neon lights without any phosphor or anything would just be red. I realized it a little bit too late, but I don't think it's a big deal. Right, that came out pretty nicely. I am super happy with the finish. I'm not so sure about the O and how I softer floating in a circle. This is a little bit bendy, but it should be fine. Yeah, let's see how this fits. So the idea is that That's it. There we go. Okay, that is most excellent. Nice. Power. Nice. All right, cool. Yeah. It's just awesome. All right, let's try to get in the heat insert and try to cramp in the battery, and then we'll see how we go. So yeah, I managed to get the PCB out. It was not as easy I would hope, but at the end, that should not be an action that you do often, so I might tweak it a little later. Anyway, cool. So let's try to put in the heat insert here. I do not have the perfect setup for that. Something I've used in the past for heat inserts is just this aluminum angle that I can, once it's almost in, I can just press on to level it entirely out and to get it very flat. I tried it before. It didn't work perfectly fine, but it's very much good enough for what I need. So here's the insert. It is just very slightly smaller here than here. So that's the part that goes in here. And it's already like somewhat guided in here. So it should be flat, and then let's try that. I have a very simple soldering iron that I really only use for heatset inserts. I put it at the lowest temperature I can get. I don't want to melt too much of the plastic, really only at that point, and I don't want to like deforming any plastic and maybe getting it in the wrong angle anyway. So this is meant for M3s, if I remember correctly. So that's not quite what we have here. We'll see how we go. All right, that worked somewhat. And et voila. Neon. It's doing its job very nicely. A last thing to do is to take a very quick look at the code. I don't want to go into too much detail. I will share the code on GitHub and put a link down in the description. If you want me to talk more about the code or any of the schematic, the PCB layout, the CAD, then please write me a comment so that I know what to focus on. One thing to mention is that we have a web server in here that serves a website. The website is written in Preact, a small version of React if you want the lightweight version of React, and compiled and then just copied over into the data directory, from where you can just copy it over via platform IO commands. The web server itself is super easy to set up and to configure. You can have API routes, you can do get, post, JSON, all that jazz. It's very powerful, and I will definitely be using it in future designs and future projects. Another thing to point out is that we are using Wi-Fi, and with Wi-Fi we want to be able to, when we get the device, set it up to connect to our home Wi-Fi. So we need to provide the SSID and the password for it to store. And what we can use here is the access point mode of the ESP32. And what's really amazing is that it can run both. It can run the access point and just a normal Wi-Fi connection. So anyway, we use the access point. Long press on one of the 4 buttons will enable the pairing mode. It enables a dedicated website that we can just open. We see the scanned Wi-Fis, can select one and then just use it. One last thing in relation to Wi-Fi to point out is that we need a way to connect the device once it's paired with our home Wi-Fi, and for that we would normally need to know the IP, but we don't have a console to just connect to it. I could try to actually display the IP on the matrix, and maybe at some point I build that. For now I'm using multicast DNS, which means you can just type neon.local in your browser and you will directly straight connect to Neon, to the device. And it's just built in ESP32. Just run it, it's done, easy peasy. So that's pretty much it. Let's take a very quick look at the web interface. So once we turn it on, there's a little status LED telling us that we're connected to Wi-Fi and everything is running as it should. We then can go to neon.local. Yeah, and here we see our pretty yellow, pretty minimalistic web interface. What we see is that our battery is pretty much empty already. We see the temperature of the battery here. I'm not entirely trusting this temperature. I think it should be 1 or 2 degrees higher, but that's fine. We have a color we can select and a brightness. I can change to a different color, and note how the moment we increase the brightness here, we see the battery temperature go up. I hope you liked it. If you did, please leave a like and subscribe. I certainly had a lot of fun creating this, and this is exactly the kind of videos I want to share on this channel. In the next couple of videos, I'm going to walk you through a project that I did a while back, which is this quadrupedal robot. I'm pretty proud of it. I designed it from scratch, and I want to talk about where it's currently at, what it can and what it can't do, and then I would love to fix a couple of things. Until then, bye.